so we can see the column.
Say again? Oh, sorry. All right. For those of you the booklets out there amongst us, let's see if I can do this with everything going on here. The plight of the bookless. All right. So how would I draw this situation out? What is it that they tell me? Thank God they tell me this. Otherwise, I really couldn't do much of anything. True. True. It's normal, right? They better give me the mean standard deviation period, but if it's not normal, I am not allowed to use what? The chart with all the answers on it, right? So thankfully, this is normally distributed. So how do I draw this situation? What goes right in the middle? 6. I love it. So the mean is 6. Standard deviation is 1 inch. So part A says, well, if one male is selected, if I take one male, what's the probability that his head breadth is less than 6.2 inches? So how do I write that down there in math? I just put, how do I translate that from English to math? What would that look like? I love it. X is less than 6.2. So in the picture, where's 6.2? I love it. So it's going to be about right there, maybe. In which way do I need to shade for this problem? Good. Below it, right? Less than. So before we can look it up in the chart, we have to do what? Beautiful. So that chart only works for z-scores, right? If I know relatively how far away I am from the average, I should know about what area there is. Because the further I get away from the average, the less area there is outside of that. So that's why that chart works the way it does. How do I set up the z-score formula for that guy? I love it. So x minus the mean over the standard deviation. So my x-score I'm interested in is 6.2 minus the mean divided by the standard deviation. That's nice. 0.2, I love it. So look that up in the z-score chart, see what you get.
Do you have extra charts?
I think I might. Oh yeah, here we go. I mean, need an extra one behind you there. Oh, I'm sure. All right. So what are you guys getting when you look up 0.2? Yeah, so 0.20, I get 0.5793, and that's the area that is where? Below it. I love it, to the left. So up on the chart, I would immediately put what I find. So anytime you draw the picture, the second you look up the z-score, you put that area up there, so it keeps you straight. Did we find the area that we need? Yes, thank God. So there's roughly what chance that some dude's head breadth is going to be less than 6.2 inches? About 58%, right? So this guy is 0.5793, about 58%. Yes, ma'am.
So you shade that area because the line goes that way because it's shaded?
Let me ask you, this line here, where'd that number come from?
From the area?
From the area, well, that is the area. Where did it come from? What did I look up to find it? The z-score, the 0.2, right? And the chart only gives me and understands areas that are below what I look up. So no matter what the question, no matter what I want, that chart's going to give me below. Some of you guys remember the shortcut I talked about. And if you understand the shortcut, cool. It doesn't really save you that much time, though. So if you don't understand it, it's fine, right? Just remember, if you look up a z-score, it gives you below. It doesn't care what you want. we have to come back then. If it would have said greater than 6.2, somebody with a big old head, I'd have to do 1 minus that to get the other side, right? Because the chart has no idea what I want. Yeah. Cool. Okay. So what about part B? Read through part B. How is that different?
It's not just one selected.
I love it.
It's 100.
I love it. And what is that a trigger for then? In fact, they do two things. They take 100 helmets, and then what's the question really say?
Less than 6.2.
Be careful now, read more than that. So they take 100 helmets, and the question they ask, how would I write the question they ask? It's different.
The mean is less than
The mean head breadth, less than 6.2. So it's still less than 6.2, but what symbol goes here?
X bar.
X bar, I love it. So remember, the two triggers. I know that section 6.4 was weird, and I know they're trying to explain when that happens is a little strange, but the trigger for us is when they take a sample and they ask a question about that sample mean. I cannot use this anymore, because this is the one that's good for individual men, right? I need the one that's good for groups of 100 dudes. So I can't use this standard deviation for that problem. This works for how far individual men are from each other. A group of 100 dudes, that whole picture should get skinny. So how do I get that new standard deviation?
1 divided by the square root of 100.
Beautiful. It's going to be all 1 divided by square root of n, so it'll be 1. And of course, square root of 100 is nice.
0.1.
You get 1/10 or 0.1. Love it. So does everybody see? The hardest part of math is knowing when to do what. So in statistics, the nice thing is, I try to desperately show you, the problem tells you when to do what. So they took a sample, they asked a question about the sample mean. I know I have to change the standard deviation so I have the right one for the problem. Now the whole problem's the same as before. That's the beautiful thing about this. I still draw my picture. If you want to make it skinnier, great, you don't have to. What goes in the middle still? Still 6. Good. Here's my 6.2. I still shade down from there, right? You want to make a z-score, but now what's the z-score formula going to be?
0.5398. Oh, no, 0.5438.
Careful now. Don't go too far ahead of me. How am I going to set up the z-score formula? What would it look like now?
X bar
Okay.
minus mean.
Over the new standard deviation. I love it. The thing I really try to stay away from, I want you to realize this, the z-score formula actually never changes. It's always the data point that I'm interested in, minus the middle, minus the mean, divided by the standard deviation I have for that problem. Right? What is the standard deviation that we have to use now? 0.1. Because I'm not in that situation anymore. I'm talking about 100 dudes. Right? So now it's going to be 6.2 minus the mean, divided by the standard deviation for this problem is 0.1. I love it. And what's that z-score going to be? Two. I love it. It should get 10 times bigger because I'm dividing by 10 times less, right? So that's a z-score of 2. So what do you get when you look at that area? When you look up 2,
0.9772.
I love it. 0.9772. All right, 2.00, 0.9772. So about almost 98% of groups of 100 men will have average head breadths less than 6.2. And if you think about it, why does that only make sense? This is the picture for individuals. Can somebody tell me how would the picture look for groups of 100? What's the main thing that happens that I keep saying? What happens to it gets skinny. Everybody rushes to the middle. So is there as much left out here? No, there's more down here then, and that's what we saw. It used to be 58%. Now it's 98% because everything rushed to the middle. There's a lot more down there. All right. I'm always hopeful. I really want you to notice the better you are at what I call a classic z-score problem, the better you'll be able to handle the tweaks we have to make. This is one tiny little tweak. Change the standard deviation. And then the whole process is the same. Cool. So any specific questions from the homework? Yeah.
Number 2.
Jeff,
Yeah.
I have a question for you guys. So let's say if we're gonna produce 100 helmets, and am I gonna produce more than at least 6.2 inch wide that will cover 98%? Or that
No,
will
be
cover
careful. The funny thing is, when I start talking about what width I want for when I produce them,
Yeah.
I don't necessarily want to have a width that'll work for groups of 100 men at a time. I want to use the individual one. Yeah, exactly. What percentage of men will be okay if I make it go up to 6.2? Maybe it's adjustable and it only goes up to 6.2. What percentage of men will be okay with that? 58%. I'm not going to talk about what percentage of groups of 100 men will be okay with it, because they wouldn't even be. It's just the average, right? If 100 men got an average of 6.2, doesn't that mean that some of them could be 7? Some of them could be 4, really tiny heads. Some could be 8, this monster melon, right? So I don't want to worry about getting the average for 100 right. I want to know what percentage of individual men would be happy with what I'm doing. So that's the one you want to use there.
So
Cool.
if I want to maximize this, let's say instead of 58, I want to make sure that at least 90% of people.
Then that's like the problem we did
I'll increase
P90, figure out the z-score for that, and then work it back to a x-score. Yeah, cool. I like it. And that's sort of like the problem we did with the doorways. How tall you want a doorway so that not so many men have to duck to get through it, right? Cool. So Sarah, which one is that?
Number 2.
2 in the same section?
Yes.
Oh, 6-4. Where am I at? Oh yeah, 2. I remember that. Okay. All right. So here's the thing. Here's the part that's really not easy to get down about section 6.4. What 6.4 is all about is just like this problem says. It's about taking groups of maybe 100 at a time, getting their average, and then plotting that, right? Before section 6.4, we were talking to individual people, and I'd say, how wide is your head? And I'd plot her head breadth, right? Which is a strange phrase, but I'd plot that. So it was for individuals. Even if I took a sample, I took this row, and I plotted everybody's individual head breadths. That's still not this section. This section is all about what do you actually plot, what actually goes into your picture, averages of groups. That's why it's called the sampling distribution of sample means. Because what actually goes into your distribution? Sample averages. Right? Take a group, get their average, plot it. Take another group, get their average, plot it. Don't just talk to individual people and plot them. So this question says, if we were to make a histogram from the data from randomly selected customers, and we find the sample mean and the standard deviation, is that what this section is all about? This is taking one sample and looking at the individuals in that sample. This section is about taking all possible samples and looking at all those averages. So that's not what this section is all about. So when they say, are we investigating the sampling distribution of the mean? No, we are not.
Why?
Because again, this section is all about when I go to Florida and I ask people how old they are and I plot their individual ages, I make it something like this. Really, a lot of young people, a lot of old people, nobody in the middle. If I go to Florida and I take groups of 20 people at a time and I ask them their age and I take an average, you with me? This picture is, how old are you? 2. And I put it, okay, there's one there. How old are you? 97. I put a 97 there. And I keep going. So I got a lot of people that are about 14 or something, and a lot of people who are about 70, right? And close to that. If I instead went to Florida and said, okay, this group of 30 people, what's your average age? And then I plot that. Where should that point most likely end up? Close to the mean, right? For a group of 30 people, their average age should be close to the real average. It's possible that I'll get a bunch of young people. How likely is that? Not very, right? That's the whole idea. So the new picture might look something more like, well, if it's 30, it'll actually look pretty much like this. Because now when I take 30, most of them should have close to the actual average. Very few should have way up or way down from it. And that kind of verifies why the standard deviation gets smaller. Because the whole thing goes, cool. Okay, hopeful. Any other specific questions from chapter 6? Okay, cool. Because I do have one section out of 6 I want to do, the last section, finish out chapter 6. And it's kind of like the next tweak to this. And the nice thing about section 6.6 is we've basically already talked about a lot of it. I don't know if you guys remember and still have this handout here. Remember this guy? This was my attempt at explaining how chapter 5 goes into chapter 6, the similarities between the two. Yeah. I think I have one extra. What's up? Okay. Thought I had one extra one here somewhere. Oh, I did. All right, but for right now, we'll just look at this. So what this one was all about was tossing a coin, flipping a coin 14 times. And of course, if I do that, how many heads would you expect to get? If I toss it 14 times, I expect to get 7. So on the chart, you can see the highest bar is right over what? 7. That only makes sense. If that's what I expect to see, it's what should happen most often. Now, we talked about this last time. This does look very normal, doesn't it? Okay. And I think I even went so far, and this could be something that would be easy to miss, I even went so far as to say, why does that look normal? One thing is the probability is 50%, which is right in the middle. It gives it room to go up and go down, right? So it can be symmetrical on both sides. If the mean was really small, let's say n is 14, what if p was 0.1? What would the mean be then? The mean here is 7 because it was 14 and 50%. What would the mean be here? What's the mean formula? NP. So what's 14 times 0.1? 1.4. So now it would be, here's 0, 1, 2. Where would the highest bar be now? Like about 1, right? Can't really do 1.4. So it'd be like 0 and then 1, and then we go down from there. Would that be normal?
No.
No. It doesn't have enough room to go up and then come back down in a nice symmetric way, right? So here's the test. And this is what we want to be specific about. When am I allowed to use the stuff we use for normal distributions? When is a given situation normal enough? And for a binomial, what I call an NPQ problem, right? If you can identify NP and Q, then it's a binomial situation. P success, Q failure. So for a binomial problem to be considered normal enough, what I mean by that is normal enough to use our z-score chart. And what's so cool about the chart is it's all the freaking answers. If I could use that bad boy, my questions get really easy. So when can I consider a binomial situation to be normal enough? It's when the mean, here, what was the problem? The mean was too small. It made it slam up against this side here, right? If the mean was too big, it would slam up against the 14 side. It would be up here, really tall, and then go down from there. That's not enough room for it to be symmetric. So NP has got to be bigger than 5, and NQ has got to be bigger than 5.
5 mean?
5. So if the mean was 5, that would give it room to build up and then come back down, right?
Is that like general for anything, or is just specific?
For the binomial situation, to be considered normal enough, that's the condition that's got to meet. Right? And what that really does is it puts the peak somewhere in the middle. So it's able to go up to it and come back down from it. If the peak is too close to one end, it's going to not have enough room to be symmetric. It's going to go start high and go low. It's not going to look normal.
I mean, the number 5, because it's pertaining to a specific problem. This one.
It's the number 5. Just like for samples. How large of a sample did I have to take for the sampling distribution to be normal? 30, 11. So if it's more than 30, that's normal. For a binomial situation, it's not talking about n now, is it? It's talking about n times p. Because it's got to put the mean somewhere in the middle like it is there, so it's got room to go up and come down.
What if I have n equal to 100, and that's 5, even more than 5 will be also to the left comparing to 100.
No, you got to be careful. Both of these keep it in check. It doesn't let it go down too far, and it doesn't let it go up too far. So if I had n equal to 100 and p is 0.1, np would be what? What's 100 times 0.1? 10. And what's nq going to be there? 100 times 0.9 is 90. And if you realize it's actually just, if this is 10, this has got to be the rest 90. Those are both bigger than 5. This situation then could be considered normal enough. Right? Okay, so that's the first piece of this, is what am I allowed to do, what I'm about to do.
Sorry, why is that considered normal? 10 and 90.
Because they're both bigger than 5.
Oh, okay.
And that again, what I really want you guys to understand is it pulls it out from that side far enough so that it's able to look normal. Because we know if it's too close to the side, it starts high and goes low. Is that normal? No. So that's if the mean is too small. And if the mean is too big, same problem. It's going to start low and just go high and then stop. That's not going to look normal. Both of these together make neither of those possible. It pulls it right in the middle somewhere so it can go up and come back down. So, let's just show you a nice concrete example of this. I don't know if you guys remember this, but last time we did, and I forgot to write it up here. I think that's it right there. The probability at most 6 heads, I think we got that. And do you remember how we did that? What's at most 6? How do I get at most 6? Add 0 through 6. Right, so if you add these up, you get 0.3946. So what we're going to do right now is to see how can you use a normal distribution to actually get that same answer, or close to it. This is one of the longest titles in history of a section. It sounds like I'm giving a speech. The normal approximation to the binomial distribution. And what I normally call this is the NAB, N-A-B, right? Just to make it quick. So if you see me say use the NAB on a test, I'm being very nice. I'm saying do this situation, what we're about to do right now. Let me ask you this. We talked about this when I did this handout the first time. What's kind of weird about 6? It's not really just 6, is it? What does it go from to?
5.5.
Yeah, it goes from 5.5 up to 6.5. So, for example, if I wanted to get up to 6, let me just do a few of these. We'll stop right there. All right, and that keeps going from there. Wow. If I wanted to do at most 6, what do I really have to go up to capture it? Which way am I going to shade, by the way, if I want to do at most 6? And you guys actually already told me that answer. You said to add 0 up to 6. I'm going to shade below it, right? So what the normal approximation does, do I really have a continuous distribution here? And what that means is my outputs for what I'm doing, can they take on any value? Remember, that's what continuous means. Can it take on any value? Could I toss 1.8 heads? No, I can't. So what's majorly wrong then about just kind of doing this. When I drew that, that is a continuous curve, right? And when we use z-scores, we know we can use 1.8972. We can use whatever we want to because it's continuous. So what the process here does is it tries to pretend like it's continuous. It's trying to make it a better estimate of the right answer. So I don't have continuous data here. I have 4, I have 5, I have 6. But how do I make it continuous? How do I slam them together? I say there is no 6. There's a situation where it goes from 5.5 to 6.5. And 5 goes from 4.5 to 5.5. So is there any gaps now? It's sort of like the same thing when we made histograms. We didn't want to have any gaps. So we had to do those class limits. Remember that? So now when I have this question, that most 6, which can be written like that in Mathish, the one tweak I have to make before I can use z-scores is to go, oh shit, I don't really have a normal distribution. It's not continuous. To pretend like it's continuous, I have to use what's called the continuity correction. I can't use the number 6 because the number 6 doesn't exist. If I shade starting here and shade down, do I include the 6?
Yes.
I don't know if you guys can see it well enough over there. Did I include the 6? No. Where do I have to start so I include the 6 bar?
6.5.
6.5. Cool. So whenever I have the nav, whenever I'm using a binomial in an NPQ situation, is not continuous. So I have to use what's called the continuity correction. I have to correct for the fact that it's not continuous. I desperately want to be able to use z-scores. Why? They're easy. I can just look them up on the chart. But z-scores only work when it's nice and continuous. Right? Yeah.
I can see what is that NP.
NPQ. So like what I call a binomial problem is an NPQ problem. Because you can identify what NP and Q are. All right, so. And the nice thing is, I am kind of nice with this, because this is a lot to take in. I'll say use the nav for this situation. And when you see me say that, that means, oh, I've got to take the whole number and go up or down by a half. Right? So what do we say this should become?
6.5.
I have to start at 6.5. So just like with taking a sample of 100 like we just did a minute ago, there was one tweak. We changed the standard deviation. Everything else was the same. With the nav, the tweak here is because the stupid thing I have is not continuous. I need to tweak it. I need to make it a little more continuous. I got to say there is no 6. There's 5.5 to 6.5, right? Just so it looks more continuous. They all slam into each other. So I have to correct for that. There's a 6.5. Now everything's the same. Now I make a z-score. How to make a z-score out of 6.5? Here's to remind you guys, this is what we got for the mean and the standard deviation last time. The 7 and the 1.871. We got a mean of 7. We're 6.5. Right there, right? So what I always do is I actually take this problem, I put a 6 here, I put a little box on it, right? Because I know I'm using the nav, I know I'm using the normal approximation. I know it really is a rectangle there. Then I just say, okay, I'm going to want to shade down. Do I want to shade from there or from there? Well, I want to include the 6, but so I better shade from here. I better shade from this side, which is 6.5. That's how I figure out which way to go. If you don't do that correction, your answer is going to be way off from what it should be. Remember, we already know what the answer should be. The answer should be 0.3946. Right? So let's see what we get here. How do I get the z-score then from 6.5? What's the formula going to be? 6.5 minus 7 divided by 1.871. I love it. Right? X minus the mean divided by the standard deviation. So help me out on that. What do you get for that? Negative. I love it. Cool. And you always want to round this to how many places? 2. So 0.27. What do you get when you look that up in the chart? Negative 0.27. .3936. And it was supposed to be what? 0.3946. Are we close? Hell yeah! Right? We got really damn close. And think about it. It's kind of weird. We use the situation that really has rectangles on that thing. Right? There are rectangles there. They're not continuous. It's 4, 5, 6. And we use a chart that only works for continuous things. And we got really damn close to the right answer. Right? So I got like a couple more minutes. Let me do one more example like this. Right? I've already bled a few people out, but I've got the practice test you probably want to get before you leave. I have to email it out to people so they'll get it. One more example, real quick. Let's say that 17% of students like parking at grocery. Right, we pick. Now here's a really good example. There's a little motivation as to why we want to do this. Because if I'm you, I might be saying, well, that's nice that it's a close answer. Why do we have to do all that crap if I could just get the answer really quick like we did? Here's an example of why. Pick 508 students. What's the probability that more than, more than, let's see, 97 of them like parking at Grossmont. Now, if you had to do this using the equation, n choose x, p to the x, q to the n minus x, how many times would you have to use the equation? More than 97 means 98, 99, 100, up to freaking 508. Do you want to do that? I'd much rather be able to just look it up on the z-score chart. First question is, am I allowed to? What do I have to check to make sure that this is normal enough to do what I desperately want to be able to do? So step 1, what's NP and what's NQ? The nice thing about the check is NP is also the mean, and I need that anyway. Right? So I'm going to get that mean out of this anyway. Yeah, so it's going to be NP is 508 times 0.17, which is
86.36.
86.36? Okay, cool. Oops, sorry. Got it. And NQ is going to be the rest, which would be 421.64, I think. Yep. All right, are those good enough? They just had to be bigger than 5. Good. So they're both bigger than 5. Check. So that means I'm allowed to do what? That means that this is what? That check means that this situation is normal enough. Good. So it's normal enough. Yeah, put the little enough. That's really what it is. What am I missing, though, to be able to do z-scores? What do I have and what am I missing that I need to be able to do z-scores? Yeah, I have the mean. What's the mean? 86.36. How do I get the standard deviation? Square root of NPQ. I love it. So what's the square root of 508 times 0.17 times 0.83? 83%, of course, would be Q. The rest, what do I get for that?
8.466.
8.466? How are we doing? Is that?
Where'd you get the 83?
If 17%
Okay.
like it,
Fine.
what percent don't? Cool, right? They got to be opposite of each other. They got to add up to be 100. Now here's what I do. Now this is exactly, the instructions would say use the NAB When I see that, when I draw my situation, what goes right in the middle? 86.36. What point am I interested in? 97. And on the 97, I draw a little bar, and on this side, I put, what goes on this side? 96.5. And on this side? And in this case, I want more than 97. Do I want to include 97? No. And which way do I want to shade? Up. So do I start here, up, or there, up?
97.
There, I like it. Right? I start here, or there, whatever I say. If I started at the back wall, it would include 97. You just told me you don't want to include 97, right? So then I make a z-score out of this, and then I look that up in the chart. Divided by the standard deviation, which was 8.466. I like it.
How did you get the 97?
Because it's from the question. More than 97, yeah. Yeah.
Will that be more precise answer if we take 97.1 and then find a z-score for that?
Not really. In fact, sometimes it would, sometimes it wouldn't. The 0.5 just makes it work for most situations. Are you guys cool with that? We didn't actually finish it out, but from there it'd be the same. Look that up, get the area, subtract it from 1 to be on that side. Right? Same situation for that. Let me give you guys a practice test, and then you are out of here.
So what is the test going to be?
The test is going to be chapter 5, chapter 6, and don't forget section 3, 5, I think it was, the one with box plots. 4? Yeah.
So I'm on 7.2.
The next class will be review day. We'll talk about formula sheet of the answer key.
Excuse me. Here's on schedule 7.3.
Yeah, we didn't make that far, so it won't be that. I was hoping to make it that far, but it just didn't happen. So now that'll be on the next test.
Our test is moved to Thursday, right?
Yep.
Next week?
All right.
Next week or Tuesday?
Lost track. Thursday, yeah. Next Tuesday's review day,
On the
and the test has been moved to the Thursday.
I know.
What's up?
The new schedule you just passed out.
I moved it twice. What do you mean to do that? When it'd be on Thursday? I gotta send an email out anyway for the people that left early and didn't get a practice test, so I'll re-verify the day of the test. Oh, that says the 3rd. It's fine. No, it's not. Just come with me to my office. What? Yeah, sure. Yeah, oh yeah. Yep. So that's the, if you did the whole x squared p of x, did the whole thing, I just skipped all that. Yeah, just to get there quick. Not very. I don't really have office hours, but I'll be there for a little bit. Oh, okay. Oh. Cool.
Yeah. Number 3 is not 5-3.
You don't want to spend.
This is a 2. So would I find the probability of not misspected? I wouldn't do that.
At least 2 leaves out what? It goes 2, 3, 4, so it leaves out 0 and 1. So you could do 1 minus the probability is 0 and the probability of 1. You guys subtract both of those off from 1.
Okay, so
It's really always, whatever the probability is, if the opposite has less stuff in it, you do 1 minus whatever the opposite is. In this case, the opposite is 0 and 1.
okay, so I would subtract the probability of 0 and the probability of 1 minus 0.
Beautiful.
Okay. Cool, thank you.
Oh yeah?